Welcome. Let's work a Lagrange multiplier example. And just to remind you of the theorem that I proved in the previous video, if we've got an extremum on a function that's restricted to a constraint curve, that's the g of x and y equals c, then the gradients will be proportional. And we can use that to identify the location of the extremum. So let's do a quick example. And the example I'm going to work for you in this video is going to be a relatively simple one, but it will show you, all the steps through the process. So we're going to maximize z subject to the constraint 2x plus y equals 100. So the thing I'm trying to maximize is this z function here. Okay, so I'm going to call that f, right? And then the constraint is 2x plus y equals 100, right? The equation that's equal to some number, that's going to be your constraint. And usually it's like, some kind of applied context, and you're, trying to maximize your production at, some kind of workplace, subject to some kind of constraint, like you only have so much money to spend. Okay, so what we know is that gradient of f is equal to lambda times the gradient of g. And so we're going to need to take those gradients. Okay, I'm going to say that gradient f equals, the partial of f with respect to x would be 2 plus 2y. And the partial with respect to y would be 2x plus 1, but maybe I'll call that 1 plus 2x, so it looks the same. Okay, then I'm going to have gradient g equaling, the partial derivative of g with respect to x is 2, and the partial derivative of g with respect to y is 1. Okay? So now I've got all of this, and I'm going to say, what am I going to say? Oh, yeah, gradient f, so 2 plus 2y equals lambda times gradient g. Well, that tells me that this, the upper component, is equal to lambda times 2, which I might call 2 lambda. And then also, I'm going to have to get that out of here and put it over there. Okay, and I also know that 1 plus 2x equals 1 lambda. Okay, really we have 3 variables, and so we would need 3 equations to get a unique solution. But our third equation is g, is that 2x plus y equals 100, and we'll go in and use that in a little bit. Okay, so my first step, I'm going to divide the first equation in gray by 2. So I'll have 1 plus y equals lambda, and I'll also have 1 plus 2x equals lambda. Okay, well, if I've got both of these things equal to lambda, I can set them equal to each other, and I can say now 1 plus y is equal to 2x, and no, 1 plus 2x. I was going to say, I know how this example is supposed to go. That wasn't going to go well. Okay, so that means that y equals 2x. Okay, now I go back to the constraint. Okay. And I'm going to say, all right, if y equals 2x, then 2x plus y, which is 2x, is going to be 100. And if 4x equals 100, then x is going to be equal to 25. Okay. And then I know that y is equal to 2x, so y is going to be 50, and the maximum value of z would be, I'll say that the maximum possible value of z is going to be z equals 2x plus 2xy plus y. Okay, so I'll have 50. 2 times 50 is 100, so that'd be 2,500, and another 100 is going to be 2,600. Okay, that's a pretty, it's pretty basic, but it overall is a typical Lagrange multiplier example in the sense that you start by setting up gradient f equals lambda gradient g, solve the system, whatever it takes to solve the system, and then you plug back in on the function to get that maximum or minimum value. Okay, but I got a little more on this. to show you what's going on here geometrically with contour map. So you'll see here I went and plotted a bunch of contours of 2x plus 2y plus y. Okay, I had them running all the way from, I think, 1200 to like 3400 or something. Got a bunch of contours in there. But now I want to also graph the constraint curve and show you what's going on. Okay, so I've got the constraint here, 2x plus y equals 100. And, well, yeah, there we go. And we can, maybe if I plot it in black, it'll be a little easier to see. And we can see that it's running through, and if you can, I don't know, if it looks like an optical illusion to you, but it looks like that line's bent to me. But if I go in and I zoom in and move it around a little bit, I'm going to note the constraint curve is tangent to the level curve at this point right here, which is, look at that, that is supposed to be, why would that be 24 and 52? It's not tangent there, it just looks like it is. The point of tangency, which it is even pointing out for me with a little dot, is 25 and 50. And it would make sense that we would have tangency to the level curves if the gradients were proportional, because we know that the, let's see, I bet that, let's see, okay, yeah, this, I had 800, so evidently I went way farther down. This is the low end, so I know that the gradient's going to be pointing out that way towards increasing f and orthogonal to level curves. Well, this black line is also a level curve, so, you know, it would make sense that their gradients would be proportional right here. Now, the fact that that spot maximizes the function in red that I'm looking at the contour map for, well, that's what I proved for you in the previous video. But I just figured I'd show you what was going on the contour map here. And, you know, I think that that's probably going to be all for this video. I worked a solid example, showed you what it meant on the contour map, and now I think you're ready to go and practice this on your own. So thanks for watching.